Good evening to all. Welcome to the fifth appointment with the PIcariello lecture on data science. Thank you for being here on this virtual channel.
Thank you very much, Neges. First of all, let me thank the speaker for being here in spite of the early morning in California. I mean, I know this is against your habits, but well, as it has become customary practice, I must do a short introduction of our speaker. And I must tell you the truth, this is quite difficult because to make a short introduction, it's not easy, even if you want to pinpoint only the most relevant contribution. Professor Djorgovski is professor of astrophysics at the California Institute of Technology, where he also founded and directs, even now, the Center for Data-Driven Discovery. He was elected a fellow of the Institute of the Advancement of Engineering and also as a fellow of the American Association for the Advancement of Science. I must say that obviously he has had many honors, but I think that the most significant ones is that the International Astronomical Union has named an asteroid after him, and there is also an entire class of globular cluster who carries his name. So this is a measure of how relevant his contribution to astronomy is. He has done many discoveries, he has pioneered the studies. Please, you are not speaking, mute to the microphone. Some of this discovery include the first studies of radio galaxies, detection of strong evolutionary effects in the galaxies, the discovery of collapsed cores in globular clusters, the discovery of the first known galaxy with a redshift larger than 3, which means at the edge of the universe. And he has done many, many things, mainly the discovery of a fundamental relation, which is called the fundamental plane of elliptical galaxies, which is even now, I mean, continues to be one of the fundamental tools we have to investigate the properties of this type of galaxies. And many, many other things. Among the last ones, the discovery of binary quasar, the first triple quasar, and what is even more important, he was the first one to demonstrate the cosmological nature of the most powerful events, energetic phenomena of the universe, the gamma ray burst. I must say that all these discoveries were due to his particular sensitivity and ability to work with data and to exploit data down to the last bit. And he has pioneered the field of digital sky survey, and this brings us to the second part of his scientific activity, because besides being a leading astronomer, he's also a leading data scientist. He was a main person between the first digital sky surveys of the entire sky, the Digital Palomar Observatory SkySire, the Palomar Quest Synoptic Sky Survey, and the Catalina Real Transient Survey, which is the last one. Obviously, by doing so, he opened the field of big data to astronomy, and immediately realized that to exploit this huge amount of data, it was necessary to change approach, and he was among the founders of the Virtual Observatory, which had the kickoff in a seminar conference, which I also attended, I think co-organized or something like that, in Pasadena in 2000, and at Caltech, and he has chaired the US National Science Definition Team for the Virtual Observatory. Finally, I must say that almost naturally from all this work, he and his collaborators were among the earliest supporters of the use of machine learning tools to exploit the huge amount of information hidden in modern astronomical data. He has been one of the founders of the emerging field of astroinformatics, and we started together a series of foundational conferences on the subject, which is the Astroinformatics Conference that only this year did not take place due to the pandemic. This is just a short summary. I must say that he is the founder of and director of the Center for Data-Driven Discovery at Caltech. And I must now add the personal comment. We have been friends and collaborators for more than 20 years, not to think about that. And I must say that the very idea of our laurea magistrale in data science, and as well as the clear-cut distinction which we operate between methodologies and domain expertise, largely stems out of the many discussions we had over the years. And this is also why George is a member of the steering committee of our master. So this is a very short summary. You can find a more detailed thing on Wikipedia, but
yes, I'm the deputy director, and I'm very happy to say a few words about our department and welcome our guest. The department is indeed the Department of Electrical Engineering and Information Technology, so it spans a wide range of disciplines, but obviously it is deeply involved in data science, both as a research topic, but also in the master degree that Professor Longo was mentioning. Indeed, we do contribute to this master program with many professors and colleagues, Flora among the others, of course. And so we really think that this is a very fundamental initiative in terms of our teaching activity. I would also like to say that our department is also the department where Professor PIcariello worked before sadly passing by a few months ago. Professor PIcariello is our colleague to whom this series of lecture is entitled, and indeed he was very much involved in this project of master degree in data science, and he firmly believed that this is a great challenge that we have to accomplish. So we are particularly grateful to Professor Longo for the fact that this series of lectures is entitled to our colleague Antonio PIcariello. And so I think I stop here, and I'm really very honored to see such a prominent speaker in this series of lecture, and I'm really convinced that it will give a very important contribution to the development of our master degree. Thank you very much for being here.
On behalf of the physics department, I'm particularly pleased to welcome you to the today 5th edition of the Antonio PIcariello lecture on data science. Well, this occasion, like Peppe just stated, gives me the opportunity to greet the speaker of today, so our distinguished colleague, Professor Djorgovski from Caltech, that already visited our department several times in past. It was the occasion for me to meet him. He combines, as Peppe just stated, the expertise in both astrophysics and data science. Well, representing the physics community in this moment, it is mandatory to say that our department is very much involved in all those activities that promotes the development of data science. In particular, I would like to remind the specific, as already done by the Vice Director of DIETI, that the specific master degree in this discipline that we offer together with other departments, in which several of our physics colleagues are involved, and the now launching PhD program in data science. The physics department considers strategic the involvement and in this kind of activity, and for this reason we hope that this research area will develop more and more in future. So please let me welcome you once again to this event and have a good seminar. Thank you.
Well, thank you. Thank you for that extremely kind introduction. And I'll just point out that none of that would have happened if I didn't have some wonderful collaborators and students along the way, including Professor Longo, believe it or not. So all that astrophysics and cosmology was fun, but now I'm doing even more fun things, and I'd like to tell you about it. So today I'd like to talk about some of the technologies and transformation that are taking place right now, which I think really will change our world, science and everything else. What I'd like to point out is it's easy to miss the fact that you live in historical times if you're in the middle of those times, because things happen adiabatically. And we do live in historically unprecedented times, thanks to the rise of information and computing technology and the web. It's like taking industrial revolution and the invention of printing press together, squeezing them in a space of a couple of decades, and then growing at an exponential pace with e-folding time, well, doubling time of about year to year and a half. Nothing like this ever happened in human history, and it has huge implications for all aspects of the society, some good, some not so good. But do be aware of this. This is when history is made, and you can be part of it. So usually people ask, well, how much data is there? It's amazingly hard to get a good estimate of that, partly because data grow exponentially, partly you have to decide what you mean by data. Raw bits, is it every pixel in every frame of every YouTube video, or something more civilized? But good rough number here is that they're about 100 zettabytes now, and that can be off by an order of magnitude easily in the up direction. And in all fields, this happens. Now, there are several important trends which I think are influencing everything else. And people focus on the growth of big data, and that's important. And indeed, data grow exponentially with more or less the same exponent as the Moore's law, for the very simple reason that the devices that produce the data follow Moore's law. And several things changed. We transitioned from data poverty to data glut. It used to be, in science certainly, who owns the data has currency of the realm. And now there is so much data that data are actually not blessing, but curse. How do you deal with it? And we also transitioned from stationary data sets to data streams, which could pouring and pouring data all the time. And if you don't analyze them in real time, you will never catch up. So the concept of data is changing. Data evolve. Not only there is more of it, but they get recalibrated, and new data get added, and so on. And so that's very different. You can't just print a table in a journal and that's it. You have to always specify which version of the data you're using. Like Sloan has every single data release online, because the results may not be different with the new data. And then we're moving from centralized to distributed resources. There's so many sources of data, and all the expertise is distributed, and you cannot have it all in one gigantic building, like data center of the world. And it's very different from the past, where individual institutions were centers for some field or another. This is now more or less gone. And because the data are cheap, what's valuable is the expertise. What do you do with the data? And every single field has those problems, or rather, positive challenges. More interesting than just data growth, in my mind, is the growth of complexity of data. I'll describe what I mean by this. But, simple stuff's already done. If you want to study complex phenomena, anything biology or society or turbulence or anything like that, you have to have complex data. So this was put in a framework of scientific paradigms by my late great friend Jim Gray. That's his picture in the last row, who divided progress of science like this. At first, there was an experimental science with Galileo and others, and then shortly thereafter, analytical theory started with Newton and Leibniz and others, and both of those have served us well and continue to serve well over centuries. Then in mid-20th century, something new and different came about, and that was numerical analysis, numerical simulations. Let's call that one Neumann paradigm. That's his picture there. And computers were used to solve a whole lot of partial differential equations at a given time, and that wasn't 1980s won't work because it just doesn't scale, both in size and complexity, and so that's where machine learning comes in and so on. And the information complexity itself is actually more subtle, but I think even more important. that we're pretty sure that there are meaningful patterns hidden in the data that humans cannot comprehend directly. They're too complex for us to grasp at once. And this is why we will inevitably need machine intelligence to augment our own intelligence to be able to see things that we couldn't see by ourselves. So just a quick comment about hypothesis-driven science or traditional mode versus data-driven science, which can be summarized in that sentence. Let the data tell you what's in the data. Traditionally, and I'm oversimplifying here, you start with some kind of hypothesis, you devise an experiment, analyze the data, and then you understand what happened. And of course, there are feedback loops all over that diagram, right? In data-driven science, you took some data, usually for some purpose, and that's by experimentalists building instruments. And then data scientists do exploration, pattern discovery, which may be biased or unbiased in different ways, and then see something, and then there is some kind of hypothesis. Why is that correlation there, or something like that? You analyze some more data, compare with the models again, and that leads to understanding. Again, feedback loops all over the diagram. So I think we are going to get in the stage where machine intelligence will earn like Nobel Prize or something like that. And in fact, I think today we have one. I'll talk about it at the end. So something else that people obsess about is, well, big data is big data. Data are actually not all that important. It's all about knowledge discovery, and data are just a step in that direction. And so there are a couple interesting things there. The first one is that information content is, for the first time, so high to enable profitable data mining. That in the past, you take data for something, there is table and journal, you do one thing you can do, and that's it. And now the same data can feed hundreds, thousands of different projects, most of which people didn't anticipate ahead of the time. And that's, of course, where we need new tools like machine learning and machine intelligence. And the underestimated factor is the data fusion, that combining different data sets can reveal knowledge that's present but not recognizable in any one of them. And in astronomy, we do this all the time by combining data from different wavelengths, and you see that there are things that are new, they look normal in one wavelength, but then look really strange when you combine them and discover new phenomena of nature like quasars and pulsars and radio galaxies. So I tried to estimate again how much data is there in astronomy. And that's surprisingly hard to do, partly because data grow exponentially, partly, what do you mean by data? And by data, I mean archive, calibrated, curated, accessible, and real archives. And my best guess is about 500 petabytes today, give or take factor of 2. And we get about petabyte a day. Most of that from large sky surveys, doubling like Moore's law, growing in complexity, and at the bottom I show some comparisons with things that may be more commonly understood. So when we talk about terabytes and petabytes, this is huge. An important one is, what's human bandwidth? It's roughly terabyte per year, geometrically speaking. Less if you read books, more if you watch videos. But it's a good number to remember. So in astronomy, we do large sky surveys. This is a synthetic picture from the Gaia satellite. And it's actually composed out of individual images of over a billion stars, 2 billion stars. And for each of them, we measure hundreds of numbers, and that's typically how it's done in sky surveys. And then we do it again and again in so-called synoptic sky surveys that patrol the sky and open to time domain astronomy. And in terms of the data fusion, well, sky looks different on different wavelengths. And if you only study in one wavelength, whether it's visible or X-ray or radio, you're missing stuff. You only see things that emit most of their energy in that waveband. But when you look it together, you have this panchromatic view of the sky, because different phenomena are manifesting themselves in different ways and they interact. And you also now a synoptic view of the sky because we repeat the measurements and see how things change. An important change also happened in theory, that now theory is expressed as data. Numerical simulations are basically produce output as data sets. And we do numerical simulations not because we're too lazy to solve differential equations, but because it's a priori impossible to solve analytically many phenomena. starting with just a simple Newtonian gravitational three-body problem, which Poincaré has demonstrated 100+ years ago does not have general analytical solution. So when you study a large-scale structure universe where each galaxy has a couple of hundred mass points and there are millions and billions of galaxies, there is no analytical solution. And this is a very simple Newtonian physics. Now, anything in biology will be vastly more complex. So we don't do numerical simulations as a crutch. We do it because it's the only way to study complex phenomena, just trying to replicate what Mother Nature does out there. And then you have to understand that and combine this with real data. This is a profound intellectual paradigm shift, which most people don't get. So in astronomy, we went through generations of technologies, but I'll skip the slide in order to save time and tell you something else. Big data is not about data, and data science is not a science. And it doesn't have its own application domain. It only becomes alive when applied in some domain, like biology with bioinformatics, astronomy with astroinformatics. And it's really a collection of methodologies, most of which come out of computer science engineering, also statistics, and then applied somewhere else. And its universality is what makes it part of new scientific method, like statistics. You know, statistics does not belong to any one field, it's a field of its own, but statistics actually has its own theorems, and data science does not. And it's a new universal language of science. We now speak the data language and data analytics language, just like the mathematics and calculus and statistics were universal languages of science. And because of that, it enables more efficient multidisciplinary, interdisciplinary collaborations, which are really interesting because all really important stuff happens on the boundaries of the fields. You know, something like climate change is not physics problem or biology problem or chemistry problem, is a whole bunch of different things that have to kind of consider together. Well, as you probably know, machine learning is now the key methodology for knowledge extraction from the data, and we use it for a variety of tasks, some of which are listed there, and there are many different challenges that are involved. But again, I suspect that you know most about this, and because I want to get to stuff you maybe don't know, I'm going to skip over that. I'm just going to give you what I see as a kind of generic machine learning discovery problem. You have some data sets, which I here represented as a cloud in pseudo 3D cube, but think of it as 3,000 dimensional hypercube, and data populated in some fashion. Most of it is not interesting at all. There are some gaps, inhomogeneities, and so on. But somewhere, in some subset of axes of feature space, in some subset of that volume, there is something that's not just noise. Correlation, clustering, something that's not just random. And that's what we're after. Now, it turns out you can't really do this in a brute force manner. This is why we need some good analytical tools. But that's what machine learning does. But there is something else. As usual, humans are the weak link in the chain. And you have to visualize. You have to see what you're doing all the time. And here I indicated roughly every step of this data to discovery process, you have to look at what you're doing. And there are two things. First, you know about good old garbage in, garbage out. If you have bad data, you get wrong results. But also, if you have good data, but choose wrong algorithms, you still get garbage out. So you have to see what you're doing. What's data distributed like? What is it? What are the questions you can ask? What tools can you use? All right. Well, that turns out to be, I think, in my mind, the single biggest bottleneck of all of data science. That how do you actually understand and control and see what's happening in many dimensions of data feature space, and you don't necessarily know a priori which ones are the interesting ones. And this mantra we always say is that you never understand anything that you cannot visualize in some way, even mathematical truth. All right, so then what can you see in your data? Well, if you're using traditional tools, you're plumb out of luck. Typically, you have one-dimensional representations like histograms or two-dimensional XY scatter plots. Unfortunately, that's not enough. If your spreadsheet contains more than 2 columns, you're plumb out of luck. And we recognize that many variables can be interacting. So people use crutches like plot a whole bunch of one-dimensional or two-dimensional diagrams, and it's just a lot of confusion, and it hides all things in projection and so on. So you can't reduce the dimensionality of the problem by projecting it down to something that's convenient, like paper or computer screen. And this is where virtual reality comes in, becoming now a very important tool for a variety of purposes. I like to see it in the context of the evolution of human-computer interfaces. Again, we do not use computers to compute. Most of the time, we use it to communicate, to discover information, interpret information. And we went from roomfuls of machinery through desktops and laptops and mobile. And now I think augmented or virtual reality or extended reality will be the next step in the way we interact with information and with computers. Throughout this evolutionary history, the power, usability, quality of information, content, all increase. So now I would say extended reality, which is any combination of fully immersive virtual reality, augmented, mixed, and so on, is becoming the new way of human-computer interaction. And it leverages multi-zillion, that's a unit, dollar investment or euro investment by the games industry. And now it's being used in a variety of fields, in science, engineering, and so on. All right, so what am I talking about this? Well, virtual reality is naturally intuitive since we're optimized to live in a 3D world. And it gives qualitatively different perception of patterns seen in the data. And it solves all the obvious problems of occultation and projection and navigation through 3D space and so on. Sometimes you just can't visualize complexity of multidimensional data space with any two-dimensional projection. And we have demonstrated through a variety of experiments that it can dramatically shorten time to insight, starting from get-go, compared how much it takes to do it with traditional tools. With most dramatic examples, we've seen change from weeks to minutes because it just lets you see right away things that you wouldn't see otherwise. Something that's curious is that my friends at JPL have created virtual Mars from rover imagery and orbital imagery. And now people who drive rovers on Mars do it in virtual reality. You put the headset on, you're standing next to the Curiosity rover on Mars. You can choose which rock to go next to. And they tested people who are doing that for a living, who usually look at the panoramic photography and then decide where to move rover next. And they divided them in two groups. One group that did exactly what they always do. The other group did it using virtual reality and asked them to estimate distances and angles of different spots. And people doing it in VR are 4 times more accurate than people doing it in traditional fashion. And they've been doing that all life versus VR people have just tried it for the first time. So that's kind of impressive. It really does bring forward that we're really optimized to do things in 3D. So there are many ways in which you can visualize data in virtual reality. It's not just the 3 dimensions X, Y, Z, but you also use shapes and sizes and colors and animate points and so on and so forth. And it's a very different experience from doing it in any other way. But it's also a collaborative experience. I mean, this is why games work. Right? It's very natural for people to interact in a virtual environment. So you can have situations where scientists or analysts are geographically distributed, maybe in some finance companies. Some of them are in London and New York and Tokyo, wherever, but they share same virtual space with their data and their tools and interact with each other, interact with the data, and interact with the tools. This is a very powerful combination that we actually commercialize in this company called Virtualytics. And we're also exploring the uses in education, like building immersive virtual reality labs where students can do things that are impossible in real life. They can shrink down to size of molecules or be bigger than galaxies. And if their chemistry experiment explodes, nobody gets hurt. And most importantly, for Caltech students, they can do this at 2 a.m. in their dorm room. And they don't have to come to class. So this is the missing link of online education. MOOCs deliver content in a scalable fashion, but could not do the labs. VR can put VR labs online. We can put real teaching labs online. And a little side project I'm doing right now, we built a virtual campus for Caltech students in virtual world of Second Life, and this is just one shot. And the purpose of it is to provide them with a safe and better way to interact and socialize in the times of pandemic. Now they're stuck in their houses and they're missing all the social components of student life, interaction, making friends, establishing new networks, learning from more older students. And Discord and other social media just don't cut it. The subjective sense of presence, even in this simplified virtual reality, is really vastly superior from, qualitative viewpoint. Okay, so let's now get into really interesting stuff. Come back to the question of data complexity. And if you think about it, the purpose of science is to replace this messy phenomenology we see all around us with a simple set of rules we call the laws of nature. And that's what we've been doing from the get-go. Apple and Moon do the same thing, law of gravity, okay? But all simple stuff's done. And so now there are probably structures in the data that we simply cannot grasp. Not just not see, but cannot grasp at all. And that's where machine intelligence comes in. So I think, and many people think, that this is maybe the single most transformative technology in the history of humanity, as important as discovery of fire, maybe more, because it changes the way we think. Well, what is it? So you ask your friendly artificial intelligence in form of Google, what is artificial intelligence? It'll tell you. Whenever you ask Google something, you're talking to machine intelligence. So here is my one slide history of artificial intelligence. It begins with Turing, with a famous Turing test. And then it was kind of getting off and on for a few decades. An important paper, it's not well known, is by JCR Licklider. It was very visionary, called Man-Computer Symbiosis, where he saw exactly where we're going, just didn't have technology to go there. And he was a DARPA project manager, and he's the one who funded the internet, so be thankful. Well, we started using these tools even in early 1990s and so on. Some important moments is 1998, computer became world chess champion, beating Garry Kasparov. Up until then, people saying, yeah, computers can crunch numbers, but they'll never be able to win chess because it's human intuition, et cetera, et cetera. Well, Garry Kasparov found that's not the case. And major milestone in 2012 with Google recognizing picture of cats. What else is internet for? But seriously, things start to pick up like 4 or 5 years ago. That first computer became world Go champion. People used to say, okay, fine, you can be chess champion, but Go is much more complex and intuitive game. Well, computer can now beat humans. And then a year later, AI that was only shown the rules of the game, not trained with any strategies or example, just shown rule of the game, invented new strategies and beat the previous AI world champion. And so we're now really moving, it's not soon, it's now, to computer-human collaborative discovery. So here is about Go and chess, and look at the quote in the lower left, that computer found solutions that humans don't see. That's what this is all about, right? Machine can think in a way that we cannot. Something a little more recent is a program called GPT-3 for Generative Pre-trained Transformer, third version, and maybe the second most impressive AI to date, created by OpenAI Institute. And there's a quote from just a week ago from the New York Times. And I really advise you to read some of these articles and read some of the text that computer has written. And it's truly impressive. Watson was nothing compared to this. But the really interesting part for me is that this program can write its own computer code. Now, this is where things get to be really interesting, because soon machines will be learning codes humans cannot understand. Well, what about understanding? Well, there was another article in the New York Times can computers devise theory of everything that physicists have been failing at for half a century? Well, maybe. But the real question is, will we be able to understand it? Because remember, we can use things even we don't understand, like quantum mechanics. Even Feynman said nobody understands it. So what if no human can understand it, no matter how hard they think or study? That's what things get to be interesting from an epistemological point of view. And the brand new thing, as of, well, people and companies been trying really hard with a lot of compute power. And now this AI can solve protein folding, which is the game changer. So this, I think, is really genuinely the first major discovery that was made purely by AI, not interaction with AI and humans. And this would be a good candidate for a Nobel Prize to be given first time for the machine intelligence. Okay, so we're talking about carbon brains and silicon brains. And thing to do is that this is a technology and it's a tool right now that enhances our abilities. But most importantly, it thinks differently. It's not about mimicking human intelligence in the machine. It's having a different kind of intelligence that humans cannot see. So I think we're already in the stage of collaborative human AI discovery with modern machine learning tools as is. But now things are getting really interesting. And another thing is that it's also going to change us as a species because we all outsource to technology things that we cannot do. You can't run as fast as a car. You cannot fly. You cannot dive as long as a submarine can. But this is the interesting one. This is technology that challenges us in our mind. And all of us have already outsourced our memory to Google anyhow. Now it's the other questions. Okay, well, Hollywood has been warning us about this for a long time. What can go wrong? I think all those cataclysmic movies and so on are really expressions of human fears based on human behavior, how humans have done things. But it need not be that way. And essentially, what we have an opportunity to do, well, necessity to do, is to develop symbiotic relationship with machine intelligence and work together. So we create technology, technology kind of creates us as well. Well, this is another interesting thing. Essentially, we created alien intelligence on planet Earth. You don't have to look for it in radio telescopes. It's right here, and it's non-human, and it's definitely intelligence. So the question is, how do we interact with it? All right, well, this is where virtual humans come in. These people are not real. These are artificially looking humans produced by Samsung's Neon lab, and they're used for a variety of things. And you might be more familiar with this phenomenon that GANs, these neural networks, can create photorealistic looking humans. They don't have to be beautiful models, just realistic looking humans by being trained on a lot of images of actual humans. And there's this website, thispersondoesnotexist.com. You can make your own fake humans. Well, okay, they come in a variety of shapes and forms and purposes. And there's a famous Princess Leia was brought from the dead to act in the Star Wars movie on the basis of previous cinematographic images of her. And they can be used as influencers, for sales, as actors and performers. I suspect before too long, human actors will be obsolete. Not only you can resurrect Marilyn Monroe or Humphrey Bogart, but you can invent new, better actors, or they'll be operated through human-computer interface in some way, or just AI. They already serve as agents and assistants, Siri, Cortana, Alexa. They will revolutionize education as artificial tutors, and so on and so forth. And Virtual humans can be powered by actual humans through the interface or by AI, by a combination thereof. So I think we are going to build something immersive 3D web equivalent. I don't know what it will be called. People call it Metaverse, cyberspace. And just like now, most human activities are in 2D web. They'll move to the 3D web. So humans can interact with this virtual world of information and entertainment and other humans and industry with their own virtual representations, their avatars, digital twins, and they identify with them. And we'll see this continuous blending of real and virtual. These people are not real either. All of them are synthetic virtual humans, and their job is to advertise stuff on social media. And they do this extremely well, which is why companies make them. But what about avatars as human representations? Well, Facebook Labs is producing some truly amazing things. They're building completely photorealistic humans representing real humans with facial expressions, gestures, and everything. They're not ready. There'll be several years before those are really released to the wild. Right now, you have to deal with cartoons. But they're possible. Those are actual synthetic images of real humans. You can do this at small scale, like the young lady on the top right shows. You can create 3D photorealistic representations. They just need to be powered by something. In the lower left, there are avatars from Second Life, and they're operated by actual humans. I have to tell you that Professor Longo's avatar doesn't look nearly as good as these two. Well, neither does mine, but anyway. And here is an interesting one on the right, from Asia, of course. This is a K-pop girl group, aespa, and they have their own avatars, and their avatars perform in their music videos. So it's human avatar joint combination. But what really caught my eye recently was a news item that they're suing somebody because they started producing deep fake videos, you know, what you create fake human video, of their avatars for pornographic purposes. So not even the real live performers, but their avatars. And I thought, wow, this really is a whole different world. All right. So these two, these are avatars created by company, or virtual humans created by a company called Soul Machines, and they serve as an interface with Watson. They're powered by AI. So you're talking through an AI to another AI as intermediary. You don't have to talk to a box. So this is where we're going. Virtual humans are the way to make AI seem more human, more acceptable, easier to deal with. And so we'll probably have this mixed reality world in which both humans and AIs can represent as virtual humans interact in some virtual space. And it would be very hard to tell apart. So you remember the 4 paradigms of science. Well, now I think we're at the dawn of the 5th paradigm. That's collaborative human AI discovery. And in think data represent just mapping of physical world into information and contain, if this is done well, phenomena known and unknown, and AI can help us find it, and can we understand it? So interesting question is, if we can't understand genuine scientific discoveries that AI makes, is that really science? Well, I mean, people use technology all the time and don't know how it works. How many people know how a cell phone works, right? Well, how do we interact with machines? Well, I believe that the optimal way to do this is through some sort of extended reality platform populated both by humans and AIs. And we're moving from information technology to cognition technology. All right, so to wrap up, here are some of my key points that we're in the middle of this fundamental transformation. Happens faster than anything else in the universe. And machine intelligence is necessary in order to actually continue exploration of complex data sets as it enhances our cognitive abilities, but now becomes an independent agent of its own. The best way we now know and demonstrated that this is the best way to represent high dimensionality data spaces is virtual reality. And together, all these technologies are really emerging in synthesis as cognition technologies. And so you will be or use virtual humans, and you will interact with other humans and artificial intelligences through that medium. So that's all I have to say. Normally, I would have stayed here to answer any questions you may have, but I'm already late for my other meetings, so I have to go. So maybe we should arrange something separately, and I'll let Sir Longo figure that one out. In the meantime, please think of good questions to ask, and you will be given an opportunity to challenge me in any of this or ask more questions. So with that, I'll really have to sign off. Too bad for the technological gaps and interruptions, but that's where we are. So thank you for the invitation once again, and I'll see you virtually some other time.
We'll organize it. Thank you very much, George. Bye.
Thank you.
So, okay, it's a pity we had no time for the questions, but if the audience agrees, we, together with the Flora, we shall organize a meeting for the people who are interested to ask a question to Professor Djorgovski, because I think that the many things he showed us are, I would say, shocking in some sense and exciting, and I think they deserve a long discussion. Comments? Flora, Christian?
I want to thank you, Professor.
Yes,
So-
Prof, I have a question for the next time. I was thinking about the fact that Professor Djorgovski show us the deep fake simulation of real people. So I would like to ask if AI can help us to solve the problem of deep fake recognition, because today is an open